Yes, we read it.
Sorry. So I will introduce Antoine very briefly. Antoine is a PhD student working with me at Imperial College London and is spending a year at the CFA. And I don't know if anyone's at the CFA, I'm sure Antoine would be happy to meet people in person. It's been kind of a quiet year to be visiting. But he's going to be talking about a project that we've been working on with Aneta and Tak on time delay estimation. So go ahead, Antoine.
Thank you, David, for the introduction, and thank you for having me give a CHASC talk. So yeah, today I'm going to talk about estimating cosmological time delays arising in gravitational lensing situations using a statistical method called continuous auto-regressive moving average processes, commonly abbreviated as KARMA. So, whoops, next slide. Okay. So first, let me introduce the gravitational lensing phenomenon. So cosmological time delays arise when you have a very luminous and distant source, for example, a quasar that emits light towards the Earth. And whenever there is an intervening object, such as a galaxy, that has a strong gravitational field, it might happen that the light rays emitted by the quasar will be bent by this strong gravitational field on their way to Earth. And what happens in this case is that the different light rays will travel along different paths, along different distances, and therefore they're going to arrive to the observer on Earth at different times. And this difference in arrival times, we're going to call it the time delay, delta, and this is the quantity that we're interested in. So for the observer, what happens is you see multiple copies of the same light curve. And if there is some variability in this light curve, well, the brightness fluctuations that you observe will be observed at different times in the different copies of the light curve. So why are we interested in this? Well, in addition to the pleasure of an interesting problem, it's been shown in the literature that measurements, so accurate measurement and estimation of cosmological time delays can be used to constrain important cosmological parameters, such as the Hubble constant, H0. So that was Revstal in 1964. So this is kind of the astrophysics motivation. And another motivation for me is that it turns out that it's actually a challenging statistical problem due to some unusual features in the data. So here I have a kind of toy example of what a time delay data set will look like. So you have two light curves, just time series of brightness measurements. And there's going to be a shift in the x-axis, the time shift between the multiple curves. And this is what we're interested in estimating. So one of the difficulties with the data is irregular sampling. So there are observational patterns that are impacted by, for example, weather conditions and stuff like that. So your time series measurements are not going to be regular. That already calls for the use of specific methods, like continuous time series models, for example. You also have big seasonal gaps, as you can see on the picture, caused by celestial cycles. And so the effect of gravitational lensing on the light curves is multiple, and there are different levels of brightness magnifications that cause the variability that you end up seeing in the data set. So the strong lensing effect causes the two light curves to have different average long-term magnitudes, which you can clearly see on the picture. And also you have additional effects such as microlensing, which adds kind of a layer of extrinsic long-term variability. So for example, here it's represented as a linear trend in both the light curves. And so you have to take all of these into account in your modeling strategy. And finally, you have measurement errors on the observations of magnitude brightness, and that are heteroscedastic. So you can see some kind of error bars around the measurements here. So heteroscedastic means that the standard deviation on the measurement error is different at every sampling time. So now let me talk about how this method, this problem, is usually tackled. You can kind of like loosely classify all the methods into two families. One, I call it non-parametric, but basically it's grid-based optimization methods. So people are trying to, shift one light curve compared to the other on a grid of time delay values and try to compute a measure of distance between the two light curves and see what value of delta minimizes this distance. So one of the problems with this method is you have one point, we have a point estimate. So you need to have something else to produce your uncertainty estimates. So usually it's through Monte Carlo simulation, which can be very expensive because you're generating synthetic light curves and kind of using your method over again on all these data sets. And you're also kind of exploring only like a discrete set of delta values. And there's a second family of methods, which I guess our method that I'm about to present belongs to. It's the methods that actually propose a statistical model for the stochastic variability of agent light curves. Sorry for the typo. So typically Bayesian or likelihood-based frameworks, which tend to be more principled and allow for a direct quantification of the uncertainty, the time delay parameter, because you're deriving a posterior distribution. You don't have to go through simulation and stuff like that. And so all those methods have been kind of surveyed and evaluated in a time delay challenge that took place in 2015, where a bunch of simulated data sets were generated by the writing team, and then participants in the challenge were using their methods on this bunch of data. And the winners, some of you might be familiar with them. It's the Cosmological collaboration at EPFL. Roughly what they're doing is they're using kind of 4 different non-parametric techniques, combining the estimates from the 4 different techniques into their final estimate. And also one entry that is noticeable is the team led by TAC in 2017, who did very well too. They came up with this Bayesian method, and they modeled the light curves using, yes, Vinay?
So maybe the reason the Cosmological did well was because of the method of light curve generation in the TDC, right? And actually, I guess this is a question for Todd. Do you remember how they actually generated the light curve stuff?
Actually, I can answer. Just make sure. Did everybody hear what Vinay said?
At least I could hear.
Yes.
Okay, perfect. Actually, it would be the other way around because the data sets were generated under the damn random walk. So if anything, it would explain why TAC did well more than Cosmogral did well. Usually Cosmogral don't make any like assumptions about the, they have different methods, but some methods don't make any assumptions about the kind of data generating process and just do like a data driven.
I remember during the time delay challenge, the Cosmogral team submitted tens of estimates while we only submitted one Beth submission. So they tried a lot of techniques, changing a little bit of their method and provided the estimate. So that means one of them just got best result. So probably they had some information that they were allowed to submit multiple submissions, multiple estimates according to a little bit different methodological tuning. But we didn't know that, so we just submitted only one, even though we have several variations according to the tuning parameters as well. That's just my excuse, but one of the Cosmogral method was based on Gaussian process with the then random covariance matrix, if I remember correctly. But most of their methods are basically non-parametric, as Antoine mentioned. So
Yeah.
the data were generated by then random process, as Antoine mentioned, which answered Vinay's question, I think.
Yeah, and if as an additional argument in favor of TAC's method, if I remember correctly, the score, like the proportion of data sets on which you gave an estimate is included in the score. So if you submitted more, you try it on more data sets, you get a higher score. Correct me if I'm wrong, Tech, but I'm pretty sure that's the case.
Yeah, that's okay.
Yeah. So I'm interested in. So yeah, I believe so. Tax method is better for the reasons I explained earlier. The Bayesian framework is more principled. You have that kind of direct quantification of the uncertainty. You're exploring the whole space of the parameter delta rather than a grid. And so the goal of this research is to improve on the Bayesian time delay estimation methods, and in two ways mostly. So obviously the accuracy of the estimates are very important for all the subsequent applications of this research, for example, for the H0 estimation. So we're trying to get more accurate estimation, but also develop a method that's going to be more applicable. I'm can dig deeper into this a bit later, but use more general models for the time series, for the light curve, so that our method can be applied to a wider range of observations. And then on top of that, trying to address some computational limitations that some current estimation techniques have. I'm also going to dig deeper into that a bit later. But so yeah, some of the limitations are, for example, in tax method, it's been shown that the DAM random walk process might have limited applicability when modeling AGN light curves. I mean, it was initially very successful, and then there's the advent of more complex models that I'm going to introduce a bit later. So one of the potential limitation is that you might be restricted in the range of observations that you can study if you have an inflexible model. All these methods, or most of them, have difficult computation usually. In the Bayesian case, you have multimodality issues, which is always a problem. And also one problem that I think is quite important is that most methods kind of rely heavily on an initial guess for delta. Their inferences are going to be very sensitive on the input of the starting value. So most methods actually require another method to compute this starting value that has to be carefully computed. So you kind of can't really use the method if you have no idea at all what the time delay may be. So we're going to try to see what we can do about this. So more into detail, as I just said, the use of the DAM random walk process to model AGN light curves restricts the range of observations that we could study. And then recently, some of you may be aware, the more flexible class of models, Karma PQ, in the astrophysics literature has been successful in modeling those types of light curves. And it's kind of a natural way for us to, natural reason to consider those models is that it seems to me that AGNs and quasars are actually sources for which this effect, the strong gravitational lensing effect, is more likely to happen because they're very luminous and very distant. So this is why we think it's a good idea to try to use those models that are supposedly better at modeling those sources. And it's kind of somewhat like a direct generalization in the way that the DAM random walk is just a Karma 1-0. So this is the kind of main contribution or main development to the Bayesian time delay estimation framework, is using this more complex intrinsic light curve model. I'm going to say in a second what that means. And yeah, with the idea that if you get a finer modeling tool, you can fit a wider range of observations. And if you can get closer to light curve data, hopefully achieve better accuracy. We're going to call our method TD Karma and refer to tax method as TD DRW, DAM random walk. Again, just going over some of the developments that we're attempting or doing. We're updating the parameter inference algorithm from MCMC to nested sampling for the reason that the multimodality in Karma PQ parameter is kind of notorious. Same for the time delay parameters. And using sampling methods that's actually designed to do that makes things a bit easier. You can identify multiple modes in the posterior distribution. And I'm going to show that there's a way of quantifying the relative probability of the modes using the output from multinest, which is typically a bit harder to do with standard MCMC methods, I think. one of the nice things as well is that the method is somehow a blind search, meaning that you don't need to impute an initial value into the method. You just need to specify the boundaries of the parameter space, which kind of lifts this limitation of previous methods of requiring this this initial value. For example, yeah, TAG was computing for multiple reasons, but one of the reasons TAG was computing the expensive profile likelihood is to get this initial value. And also, some of you may know, Multiness was actually originally designed to compute the Bayesian evidence, which can be used to perform model selection, and it kind of does it jointly with the parameter inference. So you don't need to do any kind of additional computation to have this measure of fit to do your selection. So now let's take a look at the data.
I have 2 comments.
Yes.
So one thing is about multimodality. So in Antoine's model, in our previous work in 2017, we could recognize that multimodality can happen in time-delay parameters like the capital delta. But in karma PQ model, the karma model parameters suffer from multimodality as well. So there are 2 sources of multimodality. The light curve from light curve side, there is a karma related multimodality. And for time delay modeling, there will be time delay at and the multimodality of capital delta. So if you combine these, there will be extremely complicated multimodality may happen in the parameter space in the model. And I think multi-NAS is an effective way to handle those complicated geometry of the parameter space. And another thing I want to mention is that probably this is a downside of the time delay challenge in 2013. It was from 2013. So probably it is downside that the winner, the Cosmological team, have used that method until even now. So the field, I haven't seen a new methodology for a while, but Antoine's another contribution is to introduce some advanced tool in the field because the field has been stagnated, I believe.
Yeah, thank you, Zach, for making all this clear.
Since the time delay challenge, because they were definitely the winner. The method has been used for a while, even now for about 6 to 7 years. So I think it'll be a good contribution to the field.
Thank you. Yeah, hopefully. So yes, now let's take a look at what the data looks like. So you have, assume you have n observations. Well, you have observation times, time at which you get the measurement from. You have observed magnitudes for the 2 light curves. And then, as I said earlier, you have measurement errors on those observations that come in the data in the form of standard deviations. Those are the deltas. And yeah. So now how are we going to model this data to, sorry, those are the measurement errors. Little delta.
Yeah. Oh, that.
Yeah, okay, yeah. So you have 1 vector for each of the 2 light curves. So to build our model, we're going to make a couple of assumptions. So yeah, as I said earlier, one of the problems with having irregular sampling is that you kind of have to resort to continuous tools to model your time series. The typical, I don't know, AR process, ARMA process, without the continuous aspect, assume that the measurements are equally spaced in time. So for that reason, we make the first assumption that our observations are discrete realizations of unobserved and continuous light curves, x of t and y of t, that kind of represent the true source magnitudes. And then the second assumption, the crucial one, is that one of the two light curves are time and magnitude shifted versions of one another. So, and this allows us to represent all the effects of a gravitational lensing into our model. So as I said, the first effect is that from strong lensing, you have a time shift. So you can say that yt is x t minus delta. So x is delayed by amount of delta days compared to x. Second effect, the two light curves are going to have different average magnitudes. So you can represent that by adding some intercept term, theta 0. So it's going to be the difference in average magnitudes between the two curves. And then the microlensing effect. So it manifests itself into in extrinsic long-term variability. And we're going to model this following what CHASC did using a polynomial regression. So here I'm adding this polynomial regression of order m on time, and the thetas are my microlensing, so polynomial regression coefficients. So this is equation 3 is our model to represent this gravitational lensing effect. And so from now, our plan is to use this model and kind of reconstruct the intrinsic light curve from its lens counterparts, meaning that using this model, this information, we can put the two light curves together to kind of see what would the light curve from the originating source would look like if it hadn't been lensed, for example. So there's a graphical representation of that. So the B curve, the blue curve, is shifted back by an amount delta. It's kind of small here, so you can't really see it that much. And the microlensing trends that are linear here are subtracted, and you have some kind of construction for what I'm calling the intrinsic light curve looks like. So the plan is first building this intrinsic light curve, and second, modeling that using a continuous time series process or a karma process. So this is what's happening here. And then, so here I'm just detailing exactly. So I'm calling this intrinsic light curve, sorry, Z, because each of the two light curves have n measurements. We're going to have 2 n measurements for Z. What I'm saying here in equation 4 is that I'm taking here the B curve, shifting it back by delta. So that's what the second part of my equation here for some I, etc. t minus delta. I'm just shifting y by delta, so B in the picture, and then just subtracting the relative microlensing trend to have this this vector of measurements for the intrinsic light curve. And I'm doing the same thing for the measurement errors. So I have kind of a new condition on my microlensing and time delay parameter. I have constructed this intrinsic light curve measurements. So I have my new array of times, my brightness measurements, and my measurement errors. And we're going to make the same assumption. Again, this is irregularly sampled, so we need to model it as a continuous process. So we are saying that bold Z is the discrete realization of an unobserved continuous process Z of t. And we're going to model this using a continuous process. So I think, yeah, so I'm kind of saying over again, it's what I already said, but what that means is we're going to specify a distribution for the data for our data Z given our parameters. So if you say that your time series parameters are going to be omega, we're trying to specify this conditional distribution. And I don't know why I put that there before, but the likelihood of all the model parameters is just going to be this, the distribution of our Z given our delta, theta, and omega. So basically our time delay model boils down to just modeling this, this newly constructed intrinsic light curve. And to do that, so as I said, we need a continuous process. What CHASC did a few years ago was using the damped random walk process. So it's the solution of the following stochastic differential equation. So it's kind of a mean reverting process. It's stochastically driven by this white noise process, epsilon of t, of mean 0 if and the unknown variance sigma squared. And our job here is to generalize that to the karma PQ process. solution of the stochastic differential equation in number 8. Here the alphas denote my autoregressive parameters. So in this equation, we have the dependency of the process on its last p derivatives and then the last q derivatives of the white noise process. And yeah, the betas are my moving average coefficients. So now I'm going to try to explain a little bit kind of the mechanics under those processes, and to see why we're interested in can physically motivate our choice of using karma PQ processes. So that's here is just like a kind of an introduction. I'm going a bit deeper in the next few slides, but usually you characterize the variability of those processes either in the kind of time domain using autocorrelation function, autocovariance functions, or in the frequency space using power spectral density. So the way that the damp random walk and karma process differ in their autocorrelation function is that maybe it's better to, yeah, maybe it's better I go to the next slide. I mean, it's a bit maybe too mathy, but all you need to know is that the autocorrelation function, or here it's actually the covariance, because I have, but a damn random walk process has just an exponentially decaying components with a time scale. Yeah, that's omega. That was our the time scale for which at which the process reverts back to its mean. And but the karma PQ process, the autocovariance function is actually a weighted sum, as you can see in equation 10. So you can kind of see everything else except the exponential RK tau as, so sorry, it should be Ti minus Tj as a weight, as a coefficient. And what we're interested in is actually that exponential term. So you can see the autocorrelation function as a weighted sum of exponentially decaying components, which are going to correspond to real roots in the auto-regressive polynomial. So much of the behavior of the karma process is actually regulated by the roots of the auto-regressive polynomial that I just defined here, A of Z. So when the roots are real, your exponential term is just going to be an exponential decay. That's because to enforce stationarity in the process, we enforced the real part of the roots to be negative, strictly negative. And whenever the root is complex, that exponential is an exponentially damped sinusoid. So yeah, I actually here's a picture. I'm showing 3 correlations. The gray curve is it says OU, but so OU is kind of the statistics name for the damn random walk process, Ornstein-Uhlenbeck. So you just have like a simple exponential decay. Here I have a karma 2 one that only has complex roots. So you have strictly this oscillation, periodic oscillation. And on top of this, for the karma 3 one, I'm adding a real root on the, so you have that exponential decay on top of that sinusoidal behavior. And kind of the same story if you prefer thinking in terms of frequencies. I don't know if I feel like this is pretty clear, but I mean, I get hopefully the difference between damn random walk and karma is kind of clear. And so basically we're interested in modeling our light curve with karma processes because, so for example, the PSD of a karma process is a weighted sum of you have break-like features and quasi-periodic oscillations. And those features have been kind of observed in agent optical data in the literature a little bit. And because, as I said, agents are the objects that are likely to yield, to have this, undergo this phenomenon, gravitational lensing. That's the motivation for us to use those processes that are able to capture those features in the agent variability. So all those processes, karma and damn random walk, are Gaussian processes, which mean that the conditional distribution P of Z given our model parameters is just going to be a multivariate normal distribution. So assuming you have endpoints in your endpoint realization of your Gaussian process, typically if you can evaluate the likelihood directly, this requires the inversion of an n by n covariance matrix, which scales cubically with the number of data points, which can be quite a big bottleneck. Yes, Vinay?
So I'm slightly confused. Sorry, I'm still thinking about the last couple of slides.
Oh, okay, no problem. No problem.
You mentioned that the alpha k's or the roots of the polynomial z to the k. Right?
Yeah.
But then the z are discrete. So what exactly does it mean?
Oh no, sorry. Yeah, that's bad notation on my part. The z is not the z of the time measurements. It's just a function. It could be a of x or a of whatever you want. So it's just like the polynomial. It's just like, you know, alpha 1 times x plus alpha 2 times x squared plus, that's the polynomial.
But then you can say that x and y is z still a combination of x and y.
So, sorry, no, like any variable, like
It's dummy. It can be.
yeah, it's a dummy variable.
Oh,
It's a mathematical function. Yeah, yeah. Sorry, yeah, it's bad notation. Yeah. Yeah. It's just a mathematical function. Where was it? So yeah, sorry. Yeah, if you kind of directly compute the likelihood of an endpoint multivariate normal distribution, there's going to be a computational bottleneck because it scales cubically with the number of data points. With the Vera Rubin observatory, we're expecting some longer light curves. So something that's as computationally inefficient is going to be a problem when using our time delay methodology. But luckily for us, so here I just like the equation is just kind of saying that just like factoring the likelihood and writing that normal distributions are fully specified by expectation invariance. So those are the two quantities that we need to compute their likelihood. And but yeah, Karman processes are interesting as well because they're part of a specific class of processes that allow for a more efficient computation of the likelihood, actually in linear time, ON. And that's because they admit a linear state space representation that I present here. So basically just a linear state space representation means that you can write your process as a function with two equations, one state equations, observation equation, the top equation that ties your observed values with the latent process, the state vector x, and a state equation that describes the evolution of the variable in time. And if you can write your stochastic process in this way, well, you have the Kalman filter algorithm that allows you to efficiently compute the means and variances that I said that we needed in the previous slide in a linear time, which is interesting because it makes Karman process modeling scalable to large data sets, and as a consequence, our method as well. So now, okay, I've specified the likelihood, say how we compute it. As I said earlier, we're operating under the Bayesian paradigm, so which allows us to quantify the uncertainty of the model parameters by their joint posterior distribution. So it's just Bayes' theorem. We're trying to sample from this posterior distribution. That's a function of the likelihood, the prior distribution I'm going to talk about in a second, and this marginalizing constant P of D, which is just the marginal distribution of the data. Usually you don't need to compute it to sample from the posterior distribution, but you can actually, if you can compute it, it's useful because you can use it for Bayesian model comparison in a principal way. And that's what we get out of multiness. So I'm going to talk about that in a second. And just the prior distributions. So for delta, you basically operate under the assumption that you're observing the time delay in your data set. Otherwise, there's no chance that you can actually infer it from the data. So that's what I'm saying here. You could actually, like if you wanted, you could actually make it only one-sided. If you know which light curve is ahead of the other, you can cut it to 0 or swap or the other way around. And then yeah, all the other parameters are uniform in a scale that so for the alpha parameters, as I said in the PSD, when I talked about power spectral densities, they kind of control the frequencies in the data. So we just specify uniform distributions to ensure that the range of the parameters covers the frequencies that are probed by the data. So it's actually, so there's a technicality here. We don't actually sample the alphas. We sample a reparameterized version of that, which makes it easier to enforce the stationarity constraint. But it's kind of, yeah, I'm not going to talk about it here. If you're interested, I can send you some references, but there's nothing much into it. And okay, yeah, so as I said earlier, and this is kind of a recap of what I already said, but we're using nested sampling. I'm not going to introduce really nested sampling here. It's going to take too long time. But just know that it's designed to sample from multimodal posterior distributions. And instead of evolving the path of a single particle to the parameter space like MC-MC methods or standard MC-MC at least methods do, you're starting by sampling uniformly from the prior, which means that you're actually, you don't need an initial guess for delta, and you can actually use our method without any existing knowledge of what delta is, so that you don't have any sensitivity to an initial guess at all, which is pretty great, I think. And yeah, all you need to do, as I said earlier, is specify the boundaries of the parameter space, which is what we do with our priors, and uniform. And yeah, which kind of makes our method blind search and standalone because you don't have to use another one to get an initial guess for delta. So actually, I'm thinking, am I running low on time? I feel like, should I speed up or let me check what the time is? Oh no, it's 43. Okay. Yeah, so when we're using our model, we're faced with a model selection problem, which is what is the best PQM triplet that best fits the data. So P, it's the autoregressive order, Q, the moving average order, and M, the order of the polynomial regression that we use to model microlensing. So the problem is Karma PQ models are non-nested, which kind of discards a number of standard methods that you could typically use to do your selection problem. But thankfully, with multiness, you can evaluate the Bayesian evidence. I mean, multiness evaluates the Bayesian evidence, which is here the marginal distribution of the data, and can be seen as a measure of the goodness of fit of a model to the data. What's nice about it, it's kind of principled. You can it naturally incorporates Occam's razor, which means that more complex models are penalized if they don't improve on the fit of the data to the data. And you also kind of get it for free because Multinist computes the evidence jointly to the posterior sampling. So that's also a nice feature. Another nice thing about Multinist is you can actually, so as I said, you sample from multimodal distributions, as Tak mentioned earlier. We have kind of two levels in the multimodality in this problem: the multimodality and the Karma PQ parameters. So for example, Kelly 2014, the very seminal paper, I guess, that introduced the Karma processes to the astrophysics community, they were using a parallel tempering MC-MC method. We're just using Multinist, a different thing. And you also have multimodality in your time delay parameters, so a lot of modes. And the good thing about Multiness is, so it identifies the modes in the posterior distribution, and it partitions the parameter space into regions on which the separated modes are supported, which means that you could, and it evaluates the local evidence. It's called the local evidence in the Multiness papers. It's just defined equation 16. So it's basically just your evidence, but instead of integrating over the whole parameter space, you're integrating over just the region of the parameter space on which the mode is supported. And you can actually use that to quantify the relative probability of the modes in the little equation that I wrote right there. But basically, it's just the ratio of the local evidence to the full evidence that allows you to quantify the relative probability of the mode, and it's kind of useful, as we'll see in a second. So, okay, so now you have the method exposed, and let's look at a little bit into some numerical analysis. So here is a time delay data set that's from the time delay challenge, just doubly lensed, so generated under the damn random walk process. And here are the results. So I'm fitting a bunch of different karma models, meaning different orders of P, Q, and M. So it's a simulated data, so we know the truth. We know that we're supposed to have 5.86 as a true time delay. I'm comparing, so I'm putting what Tag had in his paper and what I get from fitting Tag's model using multiness. It's slightly different, but not hugely, I guess. And yeah, we have like a bunch of different models that can get a bit closer to the truth than the karma process did. And you can also, so yeah, I have the log, natural log of the evidence also computed there. So you can see that, yeah, some of those models. So those are my 5 top models, I think it was, yes. And yeah, they all have kind of higher evidence than the text model on, or sorry, the damn random walk model, which I get is, so like the improvement is not huge, but given that the data is damn random walk, there's nothing additional to be learned basically. So we can do a little bit better because my theory is that they polluted the data in the time delay challenge. They polluted the data with a bunch of additional errors, and maybe somehow the karma process is able to sift through that. But yeah, so we can do a little bit better on damn random walk data, which is nice. And now we can go on to the real data set applications. So here is
You tried for any other cases from the TDC?
that's the only data set I had.
Because then that comes off by 2 sigma. That if the true value is 5.86, we're getting 6.3.
Yeah.
So it could be just that.
Yeah, no, no, I mean, also time delays are much harder to estimate when the time delays is closer to the observational cadence. So here, like they're kind of sampled every 3 days. And if you have something very small, it makes it harder to estimate. So that might be one reason. And yeah, just having, just looking at maybe doing better than the damn random walk benchmark. So here's a double lensed quasar dataset, HS 2209. This is kind of, I don't know, known as a kind of more difficult one to study. So yeah, I might have forgotten to say that, but yeah, here I'm comparing because as Tag said, Cosmological collaboration was the kind of big winners at the time delay challenge. And they also have estimates for all those data sets I'm looking into. So I'm comparing that to what they have. So this is the first line is the results from the Cosmological collaboration. They have -20, more plus or -5. Here's a kind of someone took one of the methods from Cosmological, made it a bit better, supposedly. That's what they get. And here I'm showing 2 models. So I fit it again like a whole array of models. I think I'm showing my best model, which is 323, and then 213. I always use it as a benchmark. I feel like it's like for like a user that starts using the method, that's kind of the simplest karma that you can use, and you have 3 orders of preliminary regression, which allows you to be sufficiently flexible if you don't really know whether there's going to be microlensing or not. And we can, I mean, our error bars are looking pretty good.
So the third argument is about the microlensing order.
I'm sorry?
So karma 213 means that number 3 is the order of microlensing polynomial reflect.
Yes.
So cubic regression, basically.
Yes.
And also Moreno in 2019 I think they picked up like Karma 2-1 as the best, kind of the most effective Karma model to analyze various quasar-like curves, I think. So probably you can justify.
Yeah, that's right, Tak.
Yeah, no,
Yeah.
exactly. And then what do we get? So the reason I tried with this data set in particular is because through private communications with TAG, I knew that the time delay package, which is the code that implements text message from the 2017 paper, was yielding inconclusive results on this observation, which I confirmed myself by trying it. And if I fit the damn random walk, the TD damn random walk method using the multiness codes, it's also, I find 10 different modes taken with values kind of all around. So here I'm listing some of the modes that I have. You don't see them on the histogram because they have very low probability. So you only see the bigger ones. And yeah, so it's a bit, yeah. And then in the table, I'm again showing what I get with a few models, and also, as I said earlier, with the evidence calculation, I can compare, I can evaluate the relative probability of the models in the same way as I evaluate the relative probability of the modes. And the damn random walk model has very low probability. I mean, the probability is nice, but you just looking at the evidence, it's I feel it's kind of clear. So now second, yeah, sorry.
I think this is a good result because our previous 2017 model couldn't analyze this data set just because whenever I started the method Meyer, it just stuck there. But it turns out that Antoine's method just identified those multiple modes, showing that, oh, the 2017 model just is stuck at some one mode. One of the modes identified by this TD karma Antoine's work. So this is good thing.
Yeah, and
I have a question in that. Sorry, in that plot, the mode which TAC finds, or the code from TDDRW, it's a larger, like it's visually, it's the orange is a larger peak than the blue, which the blue one is yours, right?
yeah.
Blue one is Antoine's, and what it means is that Antoine's method identifies multiple modes, so it spread the mass across those modes, but our 2017 work is just stuck at one mode, putting all the math near that mode, so it has high peak, but it's but based only on running our 2017 work, we are not sure that whether this mode near 20 days is correct or not.
Yeah, I mean, also, so it looks higher because, you know, I'm just plotting the histogram on my sample, but it doesn't mean that it's actually higher in the you just look at the evidence and see that it actually has much lower probability. So,
Right. So that the distinction you're making there, Antoine, is it's the mode. These are modes within model, not modes between models, right? So there's
exactly.
the one thing I'm just looking at this, so you can see that the blue curve is quite wide, and your standard deviation is 1.4. The mode at 20 it looks a lot narrower than it would be indicated by the reduction in the standard deviation in your table. Is that standard deviation across all of the modes or in just that one mode?
No, it's just that 20 mode.
Okay.
Yeah.
Just because that just looks narrower than, I mean, if the standard deviation goes down from 1.4 to 0.9, that's a 30% reduction or a third reduction, but it looks a lot narrower than that. But
yeah. Yeah. And so I have another example. That's just another doubly lensed quasar J1001. And so here, here I show an example. So I mentioned that there are multimodality in the karma parameters. Here I'm showing an example of that. So I fit a particular model. I think it was 313. And I got two modes for the karma parameters. one of the modes corresponded to power spectrum density that I show on the left panel here without a frequency, so that would be the orange one. And one mode corresponds to kind of a weird looking frequency here that has a frequency of 2 corresponding to a period of half a day. So typically, I saw in the literature that Kelly, when found also some of those similar frequencies, they would compare it to the measurement noise level, which quantifies the kind of statistical fluctuations that you get from the measurement noise. And basically, if your frequency falls below that measurement noise level, you cannot say that it's a feature of the light curve itself. It might just be something from the noise. And so for that reason, I'm discarding in this case, I'm discarding the modes or models that pick up this frequency. It's also one thing I checked to make sure that wasn't a problem. Like all the modes pick up, all the models pick up the exact same frequencies, consistency check. And here, just as an example, saying that what happens to the posterior distribution of delta if you pick up a frequency, as you can see on the right panel, it actually is going to reduce the uncertainty because it basically limits the values of delta to the multiples of those frequencies. So as you can see, like the bars, the blue bars in the histogram are separated by currently approximately 0.5 days, which is the time period that's associated with the frequency that we pick up, which so reduces the uncertainty. So if we believe, in the event that we detect a frequency that we actually believe, for example, say it lies above the measurement noise level, that'll be also an additional way in which karma processes have the ability to reduce the uncertainty, increase the accuracy of our estimation. And that is not possible using the DAM random walk model, for example. And yeah, here again, I'm comparing our output from what Cosmological got. That's the first line, a few other methods that I found. And again, 213 and 432. So yeah, 213 baseline or benchmark. And 432, I think that was the best model in terms of evidence that I got. And we're also getting some, I guess, a good reduction in the uncertainty, a value that's kind of consistent with the rest. So it's pretty nice.
Also, one thing, so our OU process was also, failed with this data set as well in 2017. I think Antoine is explaining, sorry.
Yeah, yeah, that's what I'm showing here. So kind of the same story as before, inconclusive results when using the time delay package. And using the multi-nest code, we find 20 modes, also kind of all around. I mean, maybe less all around than for the previous observation. And here I'm comparing a few models in terms of their evidence. And you can see that, so sorry, it should be, I recently switched notation, so that should be TD DRW. And the evidence in favor of this model is also much smaller than for the other models. And it's like the main mode is kind of inconsistent with all the previous analysis, which is either worrying or you found something crazy. But so yeah, this is what happens. And I think, yeah, where we can take the method even further, I think apparently, from what I understand, the computational speed is kind of is quite important for those models. One way we could further speed up the likelihood computation is using the celerity model for karma processes by Foreman-Mackey. So basically, Mr. Foreman-Mackey in 2017 came up with a way of computing the likelihood of Gaussian processes that have whose kernels have a specific form, kind of quicker than the Kalman filter. It has technically the same complexity in terms of the data points, but empirically it goes a bit quicker. and karma processes also fall into the category of Gaussian processes that that can be computed in this efficient way. So that would be like a small step to have a faster likelihood evaluation. So for now, I've only considered single band light curves. TAC in 2020 wrote a nice paper showing that he did the multi-band generalization of the damn random walk method, showing that you can get good estimates from there as well. So maybe that's also a possible research direction. And in terms of applications of this method, so as I said, we can get, so try to constrain those important cosmological parameters, H0, which is a very popular field right now. And also, I think, I don't know much about this yet, but this is something that I'll be interested in working with Aneta. Apparently, there are some time delays arising in the reverberation mapping settings. And this methodology could be used directly on this data. I think you use it to estimate black hole masses. But yeah, this is it for me. Thank you very much. Thank you.
Can I add? Oh, go ahead, Casey. Sorry.
Oh no, you go ahead first.
So one more comment about the reverberation mapping is that field is also has been stagnated for a while because the dominating method in the field is Javelin, which is based on the damped random walk process. So that paper is in 2013, and that has been used for until now. So I mean, introducing your method, I mean, applying karma model for the intrinsic variability of the light curve would be also a good improvement in the field as well.
Yeah, that's right. Very good comment.
Comment about that. I mean, part of the reason that that these methods might be stagnating is simply because there is no challenge coming in from data. So maybe what you should consider is see how your method would improve estimates, perhaps coming from future observatories.
Okay. You mean the current data doesn't have enough information?
Well, these are optical, so you might want to see how it might work with NSST.
Right.
Current methods versus new methods, there might be a larger gap.
Fair. No, yeah, that makes sense.
Okay, should I ask my question now? Who's
I
the
was going to
moderator?
say, go ahead.
Oh, yeah. Yeah, nice talk. Just to follow up on what Vinay was saying, I would caution against saying that the field is stagnated just because they haven't adopted a newer statistical method. In practice, it may mean that there's other issues or challenges in the estimation problem, which are bigger effects or bigger errors than the ones that you can solve by moving from, say, an OU process to a karma PQ process. For example, in getting the H0 estimation from time delays, a big systematic error comes from the way that you take your time delay estimate and turn it into a Hubble constant estimate. It requires you to model the lens, and there's lots of uncertainties there, which are probably bigger than the ones that you get from moving from OU to a karma model in modeling the light curve. So just keep that in mind. I think this is really interesting. That wasn't a question, that was a comment. My question is coming up, which is that, at the beginning of the talk, you mentioned there are these other methods which are, quote unquote, non-parametric, where they're not actually assuming anything about the stochastic process that generates the light curve, except for perhaps some smoothness constraints. And so intuitively, based on the existence of these other methods, I wouldn't have expected that, well, I would expect that in a lot of cases, your time delay estimate is going to be fairly insensitive to the particular details of the stochastic process that you assume, because there are methods which seem to do fine without assuming any. And so in your results, actually, I see that intuition has borne out that, for example, if you go back several slides, some of your time delay estimates don't change very much if you change the karma parameters that much. They change like a very small amount. And so I think there's a regime of where your data is good enough that what your assumptions about the underlying process don't really matter. And I kind of see that in these numbers. So I guess, in astrophysics, there's different flavors of astrophysicists. And there's, astrophysicists like Aneta who care about the statistical processes of the quasars because they tell you something about the black hole physics. But then there's cosmologists who actually don't care anything about that. All they want you to do is give you a time delay estimate that they can plug into some cosmological analysis to give you H0, and they don't care about understanding quasars at all. So I think you have to keep in mind that, well, it may not be that your particular values of the karma process, the PQ estimation, actually matter for the time delay and the cosmology, but they matter more for the people who care about understanding quasars. So there's two sides of that kind of the astrophysics. I still haven't asked a question. I guess there's a lot of commentary. So I guess my point here is that I guess you showed it in a simulated example where you had an OU process where that was generating process, and when you fit your method to it, it turned out when you look at the log evidence, you ended up, if you selected by the highest log evidence, you would end up picking a karma process which had 4 and 3 rather than 1 and 0, and it just kind of seems like this is kind of a shortcoming of a model selection approach, where you seem to be selecting a more complicated model than the true model that was there. And I was curious if you had tried the other way, where you you assume some PQM for the TD karma model under some realistic cadence, and then see if you can recover the PQ of the original generated process. Have you tried that?
Yeah, so I ran a little simulation study, generating data under DRW, karma 2.1, karma 3.1, and comparing. So of course, estimates and standard deviation, but also the proportion of. So I have replicates, right? The proportion of replicates on which the correct model has the highest evidence, etc. And so I don't have the exact figures here, so it's kind of hard to say here, but. The results that you see here are kind of consistent with the simulation study, like the karma 3.1 always. So if like the correct model always has the highest percentage of data sets on which it has the highest evidence, so compared to the data, but then it kind of the more complex models also have higher evidence on, if that makes sense. It will make a lot more sense if I actually had the table. Maybe I can.
So I mean, that is to say, you usually get the right model, but insofar as you err in favor of more complicated models.
Exactly. Very well put.
So this one, from when I looked at the simulation, from my recollection of simulation, say this is a little bit of an unusual case that mostly you find the right model.
Yeah. And also, I don't know how much of that it explains, but I guess this is also like from the time to challenge at different levels of difficulty. That's one of the highest level difficulties where the data is heavily polluted by other things. So maybe that's that causes that it's not like a pure DRW, but yeah.
Yeah. Okay. Yeah. So I think in terms of the things that you've done, which actually have a bigger effect on improving the time delay estimate, it seems like fitting more complicated karma processes that actually doesn't change your estimate that much. But actually the main advance was switching from MCMC to the nested sampling, because that allowed you to explore more modes. So I think for example, you could have just assumed the damp random walk, but then used innocent sampling to realize that there were other modes which were more important. Is that a good assessment?
No, that wouldn't work. So what you say about there's not a big change when you go in the higher levels of complexity, but when you change to 1,0 to 2,1, this is what I'm showing here. The change is actually pretty big.
But is it because the DRW TD-DRW was using MCMC before, or was this all using multinest for all the methods?
No, this is all using multinest.
So it just failed with Monte Carlo.
Yeah,
When
it completely
talk-
failed with Monte Carlo. With multinest, I can get something out of it,
Yeah.
but it's, as you can see, it's not really good.
But it is
So
true
even-
when Casey is saying among the various karma models, they're very similar, but there does seem to be a bit of a difference when you add the autocorrelation parameters, I guess it is, or autoregressive. I can't remember which one it is.
Yeah, I mean, yeah, insofar as you can see the
Yeah.
damn random walk as a karma process as well.
Mhm.
There's a difference, but I guess it happens at a kind of low level of changing P and Q, right? So if you have a big change when you change from P equals 1 to P equals 2, and then at some point the change
There's
kind of
diminishing returns for making them continually more complicated.
exactly. Thank you.
Which one has more effect, changing P from 1 to 2 or Q from 0 to 1?
2 to 1 is,
2 to 1.
I mean, 2 to 1 is more
Yeah.
more appropriate for the variability, as Moreno was showing. When you look at the quasar variability, which are not lensed quasars, just looking at the variations, typically people fit damp random walk to it, but the karma to 1 seems to be better. That's why this result is better than just simple damp random walk for these cases.
For a couple of these examples. And of course, Antoine focused on these because these are the ones that Talk identified when he did his paper as being very difficult ones. So.
Right.
Yeah, but we don't know the truth for this one. This is a real data set, right? So we know that if you change from DRW to karma 2.1, you get a different time delay, but and apparently a better evidence. But we don't know that's closer to the truth, do we?
No, but the estimate that we get from the time from karma also happens to be closer to all the other methods found. So I guess that's an additional confidence that they could all be wrong, but I guess that's always the case in real data analysis. So we have to try, I guess.
So do you have plans to go back and look at all the data from TDC?
If I get my hands on them, why not? Yeah. Sure.
What did Vinay say?
Am I planning on going back to the time delay challenge data sets and using the method more extensively?
The whole simulation, yeah.
So
That's
yeah,
a good
because I don't remember how many data sets in total there were. Maybe
So
tech,
there
but
are
like thousands.
about 5,000. All of them were generated by damn random walk process, and there were a lot of they were polluted basically because the organizers intentionally added a lot of difficulties, like removing data points, adding a lot larger measurement errors and things like that. So analyzing those time delay data sets, I don't know whether that adds some values, because the actual value is when the actual generating process is more complicated than random walk. Because if it's more complicated than random walk, the damn random walk fitting damn random walk process is misleading, but karma process may find some evidence of more complex model.
Yeah, maybe they're planning on doing a new time delay challenge with the more complicated generating process.
So I have one other question and comment, because you're using the polynomial model for microlensing, and I'm wondering how big of a difference this has on the result, because in one of the examples, earlier examples, where we were seeing the differences, the polynomial was the best fit polynomial for microlensing was 2, second order, and here is the third order. So this was in simulations that you had before. So, microlensing pollutes the data, right? So you have the variability which is generated by the quasar, but also you have this additional microlensing component on top of it. And there is a question of how to properly model it and get it out.
Right. Yeah. So in terms of how it affects the results, it depends on the data. So for this data set in particular, microlensing has a pretty strong effect. Actually, the values for lower the evidences in favor of models with lower amount of microlensing are much lower, and the inference is very different. But then it was not the in J1001 it was a bit, as you can see, like second order microlensing also did well. So here, yeah, it kind of depends on the, I guess their microlensing is pollutes to different amounts for different data, right?
It's maybe worth mentioning that in Antoine's paper, all of these tables have 12 or 15 rows, right? Because there's all these, and he's just showing you some of the highlights. And some of the karma, like karma PQ with a particular P, particular Q, particular R, still might have multiple modes as well, which further complicate things. So it's just a little bit much to put all in a talk, but it's there's a lot more detail.
Yeah.
The other thing that's worth mentioning, kind of, I'm interested in what Casey might think about this, is the other difference between these karma models and the OU model actually, and the existing like Cosmorail type methods, is even though they come up with a similar estimate of delta, we see pretty consistently we get quite a bit narrower estimates of their error. And that worried me at first because I thought we were underestimating the error. But so Antoine did a pretty robust, I guess, or significant simulation study where he found that our error bars in a simulation study do match the actual frequency, get us the right frequency coverage. So, the hope is that even if you're just trying to take this forward to H naught, if insofar as we can convince people these standard errors are trustworthy, that might still be a helpful thing to narrow it down a little bit, the uncertainty.
Yeah, I was going to ask that next because during the talk, Antoine, you were saying that you get a smaller uncertainty, and I was thinking, well, maybe that's because you're underestimating the uncertainty. But I guess you've done the analysis to at least within the assumptions of your model. Yeah. So, yeah, I mean, I think, there's the two advances here of expanding to karma and then using massive sampling. I guess now I understand that sometimes the OU is too simple, even when you're using nested sampling for everything to find the other modes. So I'm just curious how often that would occur that where the OU would give you such a drastically different estimate of the delta than a higher order karma process.
Yeah, it's hard to say. It's hard to design a simulation study, right? That
probably Antoine may already have that example because he did a lot of simulation study generating light curve from higher order karma PQ process. Definitely OU process failed in that situation, if I remember correctly, right?
Yeah, so you could look, I don't know if you've done that, Antoine, so you could look at those simulation studies as Tak was just saying, when the simulated data under a more complicated model, and then look at the OU fits and see if the estimates of delta were way off or how often they were way off.
Oh yeah, I have this. I didn't put it here, but they were systematically worse than both in terms of distance to truth and error bars.
Can I see the result when it comes to this topic? Can I see the result of the previous real data?
Yes.
So here, so you said that you ran a multi-nest for DRW. So is it true that the DFW under multi-nest only identify 3 modes, while the TD Karma more complicated model identify 10-ish modes?
No, so multi-nest for the damn random walk process identified 10 modes, but it's just that they have, so the histograms, if you just look at one color, they're they're marginalized for probability. So it's just that they're so small that you can't actually see them.
Okay, so all of them identified almost the identical 10 modes, but the DL process put somewhat majority of the mass near some of the time delay value.
No, the karma only identified the mode in blue. It wasn't multimodal in the time delay.
So DLW identified 10 modes, but those 10 modes can be different from the 10 modes identified by higher order karma model, you said?
No, karma identified only one mode.
For delta.
What is the sentence reference? The second.
Oh yeah, sorry. Yeah, so it was just a damn random walk. Yeah, the second bullet point is only for a damn random walk.
Yeah, that's not clear just looking at it, but yeah, that's right.
Yeah, sorry.
He may have found multiple modes in the karma parameters, but not for delta.
Okay.
Exactly.
The multiness identifies single mode for the higher order karma model, but there were so many possibilities if you fit the DRW model. I think this is a good selling point because once you get more complicated or more appropriate model for the variability of light content, then your model has some power to restrict the range of the time delay into some region.
Yes.
Why is 20.23 not into that list?
I forgot. No, I mean there are 10 of them, but I only wrote 5. Like I picked like different ones. Yeah, an example. Okay. Well,
Yeah, so
any more questions?
Yeah, well, this might be a comment or a question, but well, I guess this is a suggestion is that, you know, when you're looking into, you know, the effectiveness or the additional gain from using a karma PQ process rather than the OU process, it's going to depend on the cadence of your data. So essentially, if you had like perfect data where your telescope is seeing the quasar every night and is getting really good measurements with small error, I think your estimate of the time delay should be less sensitive to your assumption of the stochastic process, because on those time scales, your stochastic process is basically doing a linear interpolation between this night and Tuesday night and Wednesday night. So it matters less. Where the gain of going to a more complex process is going to be seen is when you have when your data has big gaps where you don't see data for months because of the moon, or there's more irregular sampling, basically where your observations are more spread out than the time scales of variation encoded in your karma process. So I think that's the regime where you should think about it. It might be interesting just as a check to just simulate a really, really good data set with daily sampling, where you demonstrate that the karma PQ and the OU process basically give you the same result, but then gradually degrade the data, introduce gaps and irregular cadence to show where the karma PQ process outshines the simpler model.
Yeah, that's a good idea. Thank you.
And yeah, for the kind of realistic cadence you get with LSST, I think.
Right.
Because when the data is really good, then sometimes your statistical model doesn't matter that much.
Yeah. So I mean, yeah, absolutely, I agree. I also saw in the simulation study that I did where I tried to I showed that karma were doing better. I tried to simulate the data using kind of LSST type observational cadences, following what I had read in the time delay, because I think the time delay challenge data is also simulated under, or tries to simulate under, an LSST type regime. So yeah, but no.
Oh yeah. The other thing I had probably a suggestion is that there is a question of even if your true model is a karma PQ process, how much of a time span of data you need to accurately estimate the parameters of that and select the correct order. And that's a question that has nothing to do with time delay. So if you just had one time series that was regularly sampled, typically you need to observe it long enough to see multiple fluctuations around the mean. To just, for example, for the OU process, you need to observe it fluctuate away from the mean and then return to the mean a couple times just to estimate the mean reverting timescale, for example. So similarly with karma up PQ, you probably need like a pretty long timescale where you see lots of fluctuations just to estimate the parameters. So in practice, even if you ignore the time delay problem, just with a single light curve, it's kind of interesting, like how long you actually need to observe a single time series to recover the correct model. Because with the time delay, when you introduce a time delay problem, then it makes it more complicated. So if you simplify to the case where there's no time delay, just thinking about that problem is kind of interesting.
Yeah, absolutely. I need to check. Yeah, I don't recall that being ever actually. Maybe I studied in the.
Yeah, well, there's some papers by Chris Koschenek in the literature which are like, because people are using damp random walk for quasars, they were like, well, how long do you actually need to observe the quasar in order to actually estimate recover the true parameters of the OU process properly? And they said that, well, a lot longer than people have.
Right. Fair.
And also, in Kelly, I think you mentioned this, that there is the noise level and you have to go below the noise level in order to get the frequencies right in the power spectrum. So I'm just thinking
Above, yeah.
spectrum. So there is a noise and it depends on the length of the observation, but you also have the I guess the higher frequencies where you often expect this higher order to show up in the power spectrum, and there it's difficult because you have to have it's not the longer time but the shorter time between the observations, I think.
Right. Yeah.
Okay, so we should wrap up.
It's time. Is it time to? Okay. Oh yeah. Then perfectly on time. Well, thank you very much to everyone for listening to my talk and for your helpful comments and questions. Thank you, Vijay.